Turn on noise canceling in a plane, and the engine can collapse into the background. Then the person beside you speaks, or a cup hits the tray, and the sound still cuts through. The voice is reduced too, just not in the same way. Headphones do not understand the difference between an engine and a human. The answer comes down to timing, wavelength, changing sound, and the seal around your ear. To see why, look inside the cup. First surprise, active noise cancellation does not remove the engine from the cabin. It adds another sound. A driver inside the headphone makes a controlled pressure wave called anti-noise. At your ear, the outside wave and anti-noise add together. What remains is the residual, the pressure your ear still receives. Match their size and timing well, and the residual becomes smaller. The source stays outside. The headphone controls the sum at one listening region. A typical hybrid system can use two measurements. An outward microphone hears a reference of the incoming sound. Look ahead. A controller filters it for the electronics, the tiny loudspeaker, and the space around your ear. The driver usually plays both music and anti-noise. An inward microphone measures the residual. Check the result. The controller can adapt as sound or fit changes. Engineers call these ideas feed-forward and feedback. Products arrange them differently, but this representative loop gives us the useful map. Start with the textbook case, one repeating tone at one controlled point. Copy its wave, shift it by half a cycle, and match the amplitude. Every positive pressure peak now meets a negative dip. Add the curves and the result approaches zero, destructive interference. But perfect hides two requirements. If anti-noise arrives late, peaks miss dips. If its amplitude is wrong, part remains. Real headphones must keep solving both errors as the world changes. The processor cannot simply flip microphone samples upside down. Outside sound follows a primary path to the controlled point near your ear. Anti-noise follows a different secondary path through conversion, amplifier, driver, ear cup cavity, and air. Both paths change amplitude and timing differently across frequency. So the controller filters for those paths, plays a correction, measures the residual, and adapts. The required anti-noise is not the incoming wave with a minus sign. It is the wave needed after a real chain of delays and distortion. Turn the mechanism into a race. For one representative direction, the outward microphone can provide earlier reference information, but the measurement must be converted, processed, converted again, pushed through the driver, and carried to the ear. An on-time correction meets incoming pressure in the right part of its cycle. A late correction can reinforce some sound instead. Feedback also learns from a residual that already happened. Causality therefore limits how quickly the loop can react. The same delay hurts more as frequency rises. Take an illustrative quarter millisecond. At 100 Hz, a cycle lasts 10 milliseconds, so the delay is only 9 degrees. At 1000 Hz, a cycle lasts 1 millisecond, and the identical delay is 90 degrees, a quarter cycle. The hardware did not become slower. The wave gave it less time. An error that leaves a low tone mostly opposed can put a higher tone badly out of phase. This is one reason active control is strongest where waves change more slowly. Timing is only half the problem. Cancellation is spatial. The inward microphone and eardrum are close, but not the same point. With a long wavelength, their separation is a small fraction of the wave, so pressure can be similar at both positions. With a short wavelength, the same distance is a larger fraction of a cycle. Reflections complicate the field further. A low residual at the microphone does not guarantee the same residual at the eardrum. This conceptual pressure field explains why ANC creates a quiet region, not silence throughout the room. Return to the plane. Engine and road rumble contain strong, sustained, low-frequency components. Their long cycles give the controller continuity, and long wavelengths make nearby points more alike. Speech spans many frequencies, with starts, stops, consonants, vowels, and rapid changes. ANC can reduce its lower frequency parts, so the voice really becomes quieter. But faster components are less forgiving of delay and position, and enough spectral and temporal cues can remain for words to stay intelligible. A sharp clink is harder again. Much of its information arrives before an adaptive loop has much history. The system is not choosing what matters. Different signals expose different physical limits. Headphones have a second defense needing no anti-noise. Ear tips, cushions, the cup, and surrounding materials physically reduce outside sound. That is passive isolation. It varies with frequency, but complements active control. Electronics are especially useful against sustained low-frequency noise. The physical barrier helps with components the loop cannot follow as effectively. What you experience is therefore an active electronic layer combined with a passive mechanical layer, not one universal eraser. The physical layer explains why fit matters. Open a leak around a cushion or use an ear tip that does not seal, and outside pressure gains a new path. The acoustic load on the driver changes too, so anti-noise calculated for one fit may not match another. Glasses, a loose cup, or the wrong tip size can change the result. Before judging the electronics, improve the seal. It is part of the controlled acoustic system. The complete model is a loop. Measure incoming sound, filter for the real paths, play anti-noise, check the residual, then adapt. It works best when sound gives the system time, wavelengths are forgiving, and the seal is stable. Use ANC for aircraft, trains, fans, and road rumble, but expect voices and sudden sounds to behave differently. And remember, consumer ANC is not automatically certified hearing protection. In hazardous noise, use properly rated protection. That is the system working inside the quiet. Subscribe to Offscreen Works and we will open another hidden system next.